In September of 2013, a physicist stood up in front of a room full of reporters at NASA, pressed play on a short audio clip, and told everyone listening that what they were about to hear was historic. What came out of the speakers wasn't a voice, and it wasn't music. It was a low, eerie, rising tone, something between a hum and a wail, climbing steadily in pitch over several seconds before settling back down. The kind of sound that could just as easily have been mistaken for a sound effect out of a low-budget science fiction film as for genuine data collected by a real spacecraft. He told the room, plainly, that this was the sound of interstellar space. Reporters in the room, and millions of people who heard the recording afterward, were left with an obvious, nagging question. Space is supposed to be silent, so what exactly were they actually listening to and buried? Underneath that eerie recording was something even stranger. The sound hadn't been made out here at the edge of everything humanity has ever explored. It had been made by our own sun, more than a year earlier, in a violent outburst so powerful it took 13 months just to cross the tens of billions of miles separating. Our star from the spacecraft that finally heard it scream. This is the true story of how Voyager 1 recorded the sound of our own sun's fury, echoing out into the dark long after the sun itself had already moved on, and why scientists are still listening for more of those screams today. To understand what actually happened here, you first need to understand what Voyager 1's instruments can and cannot detect, because the phrase sound of interstellar space is a little bit of a shortcut, and the real explanation is stranger and more interesting than the shortcut lets on. In the vacuum of space, there is no air, and without air, there is no sound in the way we normally understand it. The old line from science fiction, "In space, no one can hear you scream," is technically correct. Sound, in the everyday sense, needs some kind of physics-AOL medium, molecules of air or water bumping into each other in a chain reaction, to carry a vibration from one place to another, and interstellar space is simply too empty for that kind of chain reaction to happen the way it does here on Earth. Voyager 1 does not carry a microphone, and it never has. What it carries instead is an instrument called the plasma wave subsystem, a pair of thin antennas extending about 30 feet out behind the spacecraft, originally designed by physicist Donald Gurnett of the University of Iowa, who spent decades as the principal investigator on that exact instrument. Those antennas don't listen for sound waves. They measure tiny variations in the electric field of the plasma surrounding the spacecraft, the charged, ionized gas that fills the space between stars. When that plasma gets disturbed, its electrons ring, oscillating back and forth at a specific frequency that depends directly on how densely packed those electrons happen to be, similar in principle to how a struck bell rings at a pitch determined by its size and shape. That electrical ringing happens to fall within the same general frequency range as audible sound, which means scientists can take the raw electrical data and simply convert it directly into an audio signal, letting human ears listen to something that was never actually a sound wave traveling through air at all, but a genuine, measurable disturbance in space itself, translated into a form we're equipped to understand. Voyager 1 crossed the heliopause, the outer boundary of our sun's protective bubble, in August of 2012, becoming the first human-made object in history to leave the solar system and enter true interstellar space. But because of how the mission's data storage and transmission worked, and how far away the spacecraft already was, NASA didn't actually confirm that historic crossing until nearly a year later in the summer of 2013, once months-old recorded data finally made its slow way back to Gurnett's desk at the University of Iowa. Voyager's data storage system, technology dating back to the 1970s, recorded information onto tape rather than transmitting it instantly, and that stored data typically only got played back and sent to Earth every 3 to 6 months. Meaning the spacecraft could have already made history months before anyone on the ground had any idea it had happened. What convinced Gurnett wasn't a single dramatic reading. It was 2 separate episodes of plasma oscillation, one recorded between October and November of 2012, and a second recorded between April and May of 2013, both showing the exact same telltale signature, a rising tone climbing steadily, upward as it played out, indicating that the plasma being measured was growing denser and denser, exactly what you'd expect once the spacecraft had genuinely crossed into thicker interstellar space rather than the thin, sparse solar wind still found inside the heliosphere. Here's where the story gets genuinely strange, and it's the part that gives this whole thing its title. That second event, the one recorded in the spring of 2013, wasn't caused by anything happening near Voyager 1 at that moment. It was the delayed, arriving echo of something that had happened back at our own sun more than a year earlier. In March of 2012, the sun produced a massive eruption, a coronal mass ejection, an enormous outburst of charged particles and magnetic energy hurled outward from the sun's surface with tremendous force. The kind of event that briefly turns a calm, stable region of the sun's outer atmosphere into something closer to a cannon firing billions of tons of superheated material directly into space. Events like that happen. regularly enough that they rarely make headlines outside of dedicated space weather circles, but the physical violence involved is almost impossible to overstate. An eruption capable of releasing more energy in a matter of minutes than humanity has produced across its entire recorded history combined. That burst of solar material didn't stay near the sun. It kept traveling outward, plowing through the solar system, passing every planet, crossing the orbit of Pluto, continuing on and on through the thinning edge of the solar wind, moving at speeds of well over 1,000,000 miles an hour, and yet still requiring more than a full year to cover the immense distance involved. And finally, after 13 months of travel across roughly 11 billion miles of space, it reached Voyager 1, sitting quietly in interstellar space, and slammed into the plasma surrounding it hard enough to make the local electrons ring audibly in the spacecraft's instruments. That's the scream in this story, quite literally. Our own star had thrown a violent, genuinely enormous tantrum back in March of 2012, and more than a year later, tens of billions of miles from where it happened, an aging spacecraft built in the 1978s heard the delayed echo of that outburst finally arrive and shake the space around it. Gurnett himself, describing the discovery, made clear that what the instrument had captured wasn't sound in any conventional sense, but he also didn't hesitate to call it music, in his own way, the kind of description that only makes sense once you understand that space, far from being the silent, empty void popular culture usually depicts, is actually full of exactly this kind of physical activity, constantly rippling with energy released by our own star and by others, scattered throughout the galaxy, simply waiting for the right instrument in the right place to translate that activity into something we can perceive. At the same 2013 press conference, Gurnett told the assembled reporters directly that when they heard the recording, they should recognize it as a genuinely historic event, the first time humanity had ever managed to record anything resembling sound from within interstellar space itself, a milestone that had taken 36 years of continuous spaceflight to reach. It's worth remembering, too, that Voyager 1's dedicated plasma density instrument had actually failed decades earlier, not long after its Saturn flyby in 1980, which means T. Gurnett's team had no direct way to simply read off the plasma density around the spacecraft. They had to get creative, waiting for exactly this kind of solar-triggered disturbance to make the surrounding plasma ring, then working backward mathematically, from the pitch of that ringing to calculate what density of plasma must have been present to produce it. If this were the end of the story, it would already be a fairly remarkable piece of space history. But Voyager 1 kept listening long after that first announcement in 2013, and what it heard in the years that followed turned out to be even stranger and considerably more persistent than a single delayed echo of one solar outburst. Starting in 2017, the same plasma wave instrument began detecting something researchers hadn't previously identified, not a brief, rising tone tied to one specific solar event, but a finite, narrow, continuous hum showing up again and again, year after year, in the background of the spacecraft's readings, unlike anything the two dramatic 2012 and 2013 recordings had prepared anyone to expect. Unlike the two dramatic episodes that confirmed the heliopause crossing back in 2012 and 2013, each of which faded away after a matter of weeks once. The triggering solar disturbance had passed through. This new signal simply persisted, refusing to fade the way theory said it should, a low, steady murmur stretching across a region of interstellar space more than 900 million miles wide, according to research eventually published in the journal Nature Astronomy by a team led by researcher Stella Koch-Acker at Cornell University. Where the earlier recordings had captured a single dramatic scream arriving from a specific, identifiable outburst, this newer signal looked more like the ongoing ambient hum of interstellar space itself, constantly humming with structure and turbulence that decades of theoretical modeling had never predicted would actually be. There, evidence that the space beyond our sun's influence isn't the calm, mostly empty backdrop generations of physicists had assumed it would be. The story didn't stop with that persistent hum either. In 2020, Voyager 1's instruments picked up something new again, a distinct pressure front sweeping past the spacecraft over the course of about 8 days. Another echo of solar activity arriving from tens of billions of miles loser to home, this time causing the local magnetic field strength to spike abruptly by more than a third almost instantly, and then, strangely, keep climbing for more than a year afterward before finally beginning to settle back down, a slow-building disturbance researchers eventually nicknamed the magnetic hump. It behaved less like a scream that arrives, echoes briefly, and fades, and more like a scream that somehow kept building in intensity long after the moment it first reached the spacecraft, defying the straightforward decay pattern every earlier disturbance had followed. Even stranger, when scientists went back and checked that disturbed region of space again in 2025, 5 full years after the original event, they found it still hadn't fully returned to the condition it was in before the disturbance arrived. Evidence that a single burst of solar activity, one more scream from our own star, may have left something behind that genuinely altered the character of the interstellar environment for years, rather than simply passing through and fading away the way anyone would have expected. Put all of these events together, and a genuinely remarkable pattern starts to emerge, one that reframes the entire original 2013 announcement in a much bigger context. Voyager 1 isn't just an instrument that happened to catch one dramatic recording back in 2013 and then went quiet. It has spent more than a decade since that first announcement continuing to listen and continuing to catch echoes of our own sun's ongoing activity, delayed by months or years, arriving from tens of billions of miles away, each one adding another piece to an unprecedented real-time picture of how far our star's influence actually reaches and how it behaves once it finally crosses into the space between the stars. Our sun isn't a single one-time source of that original scream heard back in 2013. It's an active, ongoing source of disturbances, releasing outbursts on a regular basis, and Voyager 1 happens to be sitting in exactly the right place, with exactly the right kind of aging but still functional instrument, to keep hearing them arrive, one delayed scream at a time, for as long as its dwindling power supply allows it to keep listening. Every recording that instrument has ever captured, from that first eerie rising tone in 2013 to the persistent hum discovered in 2017 to the still lingering magnetic. Hum from 2020 tells essentially the same underlying story from a slightly different angle. Our sun is loud, our sun is active, and the space it disturbs on its way outward extends far, far beyond anything early models of the solar system's edge ever predicted it would. That timing matters more right now than it has in years, because our sun doesn't produce these outbursts at a constant, steady rate. Solar activity rises and falls across an 11-year cycle, swinging between quiet minimums and violent maximums when sunspots multiply and eruptions become dramatically more frequent. And the current cycle, known to researchers as Solar Cycle 25 star, reached its predicted peak of activity around the middle of 2025, meaning the sun has spent the past year or so producing a noticeably higher rate of exactly the kind of violent eruptions capable of eventually reaching Voyager 1 and making the surrounding plasma ring once again. Every one of those eruptions is, in a very real sense, a fresh scream currently in transit, somewhere in the vast gap between the sun and interstellar space, traveling outward on a journey that could take well over a year to complete, due to arrive and register in Voyager 1's instruments at some point over the following months or years, assuming the aging spacecraft and its equally aging plasma wave instrument are both still functioning by the time each disturbance finally catches up to it. Voyager 1's twin, Voyager 2, still carries a working direct plasma density instrument, unlike Voyager 1's, which failed decades ago, and researchers modeling this same pattern have projected that Voyager 2 may catch a comparable disturbance of its own sometime around 2024 to 2025, offering a fresh, independent chance to confirm exactly how these delayed solar echoes actually behave once they finally arrive at the edge of known space. There's something worth sitting with in the fact that this entire body of work traces back to a single instrument built and designed by one scientist, Donald Gurnett, who spent essentially his entire career listening to exactly this kind of signal, from Voyager's earliest days flying past Jupiter and Saturn all the way through its historic crossing into interstellar space and beyond. Gurnett passed away in 2022, having lived to see his instrument confirm not just the original heliopause crossing, but the beginning of the persistent hum discovered in 2017. An entire body of discovery built on hardware he helped design decades before anyone could have known just how much it would eventually reveal about how far and how persistently our own star's violence actually travels. His colleagues, including longtime collaborator William Kurth, have continued that same work in the years since, still combing through fresh data as it arrives, still listening for the next scream to show up in the readings, carrying forward a research program that began before most of the people currently working on it were even born. Here's what's genuinely worth taking away from all of this. Our sun is not a calm, quiet, distant light sitting peacefully at the center of our solar system. It is an active, occasionally violent star, regularly hurling enormous outbursts of energy and charged particles outward in every direction, and most of the time, we simply never notice, because those outbursts either miss Earth entirely, or arrive here as nothing more than a pretty aurora glowing faintly near the poles, a gentle, harmless light show standing in for the same kind of violence that, tens of billions of miles away, is enough to make an entire region of interstellar plasma ring audibly. But tens of billions of miles away, in the genuine darkness between the stars, an aging spacecraft built before most of the scientists currently studying its data were even born, has spent more than a decade patiently listening for those same outbursts to arrive, translating the electrical ringing of disturbed plasma into something we can actually hear, turning our own sun's distant, delayed tantrums into an eerie, rising tone humanity first heard played out loud in a NASA conference room back in 2013, and has kept hearing, in one form or another, ever since. If stories like this are what you come here for, hit subscribe, turn on notifications, and let me know in the comments whether you've ever actually listened to NASA's original 2013 recording of interstellar space. Because once you understand what you're actually hearing, it never quite sounds the same way twice.